sorry. The electrons vary in the amount of energy they possess, and they occur at certain energy levels. And we talked about how the closer you are to the nucleus, so the lower the energy level, right? The less the energy. So that the electrons require, so, or possess. In this case, let's see what else. Next is that is what determines how an atom behaves or bonds when it encounters other atoms. So remember that the first shell can only hold 2 electrons. And after that, 8 or 32 or however many. But the main thing is that the first 2 rows of elements, or 3 rows of elements, I think it is, or maybe it's 2. No, it's 3. 3 rows of elements. You have all the way to argon are going to be okay to do a Lewis structure. But after that, you cannot do that because you have the d electrons and that doesn't work. So I had to drink some water. Anyway, so carbon, remember the group number is what determines how many electrons are in the, well, not determines, more like reveals to you how many electrons are in the outer shell. So carbon, which has 4 electrons, would either lose or gain 4 electrons. Nitrogen, who has 5 electrons on the outer shell, will gain 3 electrons to make 8. Remember, this is what we're all looking for. And oxygen, which has 6, because it is in group 6A, it would gain 2. And of course, the charges would be negative, because if you're gaining, you're going to go negative. If you're losing, you're going to go positive. All right, why are electrons so important? Like I was telling you, it's because you have bonding with them. The only ones that really are most important, well, not the only ones, but the ones that are most important are the outer shell electrons, also known as valence electrons. Now, the energy of those electrons is determined by the levels that are beneath it, but the way that they bond is determined by how many electrons you have. So right here, it's a quick representation of all of the first, like I said, the first 3 that have Bohr models, because after that it doesn't work. So, okay, so this is the other thing. We make what is known as any Lewis dot structure, or Lewis structure for short, or electron dot structure in this case, is basically all you're doing is you take the symbol of the atom and you put the dots around them representing the electrons that are on the outer shell. So if you're in group 1, you're going to have 1 dot. If you're in group 2, you're going to have 2 dots. And notice they're not paired, and there's a reason. If you have 3, you're going to have 3 dots. If you have 4, 4 dots. And now they're pairing, because 15 would have 5 dots, and you would put 1 on each cardinal, basically north, south, east, and west of on the end, right? So north of the end, south of the end, and east of the end, like that. Okay, so all of that, and then repeat as you get more. So if you have 5, then one of them is going to be paired. The same thing with 6, with 7, and with 8, they're all paired. All right. And let's see what else we got. Okay, so when we have bonding, we can have different types of bonding. We can have ionic bonding, which is a total transfer of electrons. Covalent bonding, which is a sharing of those electrons. And metallic, which is delocalized electron, and is really a weird looking bond, but it is I mean, it is not a true chemical bond, but it is probably the strongest. All right, so if you were to look at that dot formula without any element under it, which element should be there, right? Based on what we said, we are looking at one dot. Therefore, any element in group 1A would qualify. So sodium and potassium. B, you can count the dots, there's 5. So this is 5A. Therefore, nitrogen and phosphorus would qualify. All right, now that's to wake you up. Okay, so ionic bonds are formed between two ions by the total transfer of electrons. So what does that mean? That means that if you're a metal, you're going to give the non-metal your valence electrons. And the non-metal is going to take them completely into their shell. So that is what is known as an ionic bond, because both of them form ions as they are doing the bond. And once they have formed the ions, they are held together by what is known as an ionic bond, which is electrostatic form of attraction. So what does that mean? That means a positive attracts negative, right? That's all it means. It's just like magnets. All right. But in this case, it's an electric charge, therefore it's called electrostatic. Okay, so if the delta electronegativity is greater than 2, the bond is usually ionic. Now, I am saying usually because, as you know, there are exceptions to any rule, and there are some that are lower than 2 that are ionic. But as a general rule, this works. And the most important part here is that the elements involved, okay, this is the most important part. The elements involved are a metal, right here, and a non-metal. And that's how you know you have an ionic bond, because you have a metal and a non-metal in a compound. All right, so let's keep going. All right, so this is just a quick thing to remember, that ionic bonds, they're like their electrons taken, not shared, right? So that's kind of what James Bond says when he talks about himself, except he says martinis, shaken, not stirred. So it's kind of like I said, to remember. All right, the formation of ions from metals. How do we form ions? Again, it all happens by the group number. So if you are a metal, you are going to always lose electrons. And remember, metals are to the left of the little stair step on the periodic table. Okay, so they're going to form positive ions. And you notice that the group number kind of determines the ion charge. So if you're a group 1 metal, you're going to form a 1 plus. If you're a group 2, you're going to form a 2 plus. And this says 13, but 13 is also 3A. So again, a 3 plus. So looking at that, let's look at why that is. Okay, so you've got sodium atom that is going to lose an electron, right? So you got 2, 8, and 1. And the one that is going to lose is always going to be your outer electron. So, but we're not yet losing it. So here's the atom, which we have 11 protons and 11 electrons. And there, one's positive, one's negative, therefore charge becomes 0. Over here, we have a sodium ion. You notice there's a charge. Why is it positive? Because now we have 10 electrons, but we still have 11 protons, because protons never change. So when you subtract them, you get a positive 1. And there's the charge. Okay. So let's look at what this means. All right, magnesium, same thing, right? Magnesium has 12. It's in group 2. See how you have 2 little electrons? So now those 2 electrons are going to be lost. And you get a magnesium plus 2. And it has 10 electrons and 12 protons. Again, 2 positive. Okay. So these are some typical ions with positive charges right here. And their group number. As you can see, the group matches the charge. And like I said, group 13 is also group 3A, which is also matching. All right, so looking at this, if you have a number, if you have aluminum, how many valence electrons would you have? So you go look to your periodic table and you find aluminum is in group 3A. So the answer is 3. What is going to be the change in the electrons? Well, since it is in group 3, it is going to lose 3 electrons since it is a metal. And the last thing, what is the charge for that aluminum? Since it lost the electrons and it has more protons than electrons, and protons are positive, the answer is 3. You see that? And there's your answer. So if you ever want to do this PowerPoint and ask your own questions as you are looking at it, and answer, your own questions as you're looking at it, you always have the answer at the end. All right, again, given the ionic charge for each of the following, which one of these would have 12 protons and 10 electrons? Well, again, 12 minus 10 is 2. So we have 2 positives in it. Okay, hold on. Somebody is in here. Okay, there we go. I got him in. All right. Next, we have 50. So 50 positives and 46 negatives, right? So 50 protons and 46 electrons will give you a positive 4 charge because you have more positives than negatives. And 15 protons and 18 electrons. Now look at this. This one doesn't match what we were learning, but you can still figure it out because positive and negative. So now you're going to have a surplus of negatives. Therefore, it's going to be 3 negative. All right. And that's how that works. All right. So if you have a nonmetal, they're going to gain. And when they gain, they are going to become negative. So groups 5A, 6A, and 7A, remember they're 15, 16, and 17 without the A's, are going to form non-metallic ions where charge of -3 respectively, right? -2 and -1. So to look at this, remember how we did the Lewis structure with the number of electrons around it that are on the outer shell, which is what we know here, right? So we know that we have 7 because in group 7, therefore, we are going to gain 1. That's it, just 1. That's all we gain. Why do we only gain 1? Because there's not enough room to put 2, because there are not going to be 2 electrons on the outer shell of this. 2 more electrons, because that would give it 9 on the outer shell. And you have to stay with the octet. Octet meaning 8. Therefore, now you have 8 electrons around it, and you have a -1 charge. And look at how the math goes. You have 9 protons normally, but now with the gain of 1 electron, we have 10. When we subtract the 10 negative plus, if you subtract 10 minus 9, it gives you 1, but the 1 is negative charge because it's an electron. All right, so let's keep going. Now, again, the ionic bond is formed between metals and nonmetals with very different electronegativity. Remember, it was above 2.0 as a general rule. change, the difference in electronegativity. All right. The bond is formed by a total transfer of electrons from the metal to the nonmetal. And this is the result. So these are characteristics of ionic compounds. They produce charged ions in all states. So basically, whether it's solid, liquid, or gas, they're still going to be charged. And they are very good conductors of electricity, and they have a very high melting point. If you've ever tried to melt salt, like you melt sugar on a skillet, it will not work. Salt is an ionic compound, and it has a very high melting point, certainly higher than what we can produce on a stove. It'll just turn black. That's what it does, because and even if you really heat it, it'll turn black. But I think on the stove, it doesn't do anything. So an example of it is sodium chloride, which is table salt, calcium chloride, and potassium oxide. Here's a representation of that bond happening. You notice how the ion, which is uncharged, and the atoms, that are uncharged, once they transfer the electrons, one becomes a positive, which is the metal, and the chlorine becomes negative. And when you name the ions, when you're naming compounds, you use the name of the two ions. So the name of the positive ion always goes first, and that would be sodium. And the name of the negative atom goes last. And when a negative atom changes into an ion, right? An atom changes into a negative ion, that means it changes its name. Instead of being chlorine, it is now known as the chloride, IDE, ending ion. So, therefore, the name of this compound is sodium chloride. All right, and here's another look at what that would look like. So you notice that once they are separated, their ions, and they're charged as a separate ion, it's zero, it's 1 and -1. But once they get together, and that's the main thing, that you always want an ionic bond to end up in a compound that has no charge. So it's neutral, right? Therefore, your positive and your negatives have to be the same. And that's what we're going to learn later here in a minute. Okay, so this is in Lewis structure form. You have the one electron of sodium transferring into the last or valence electron level of chlorine. Sodium becomes an ion, it loses that level, and it gets a positive charge. And chloride, see, there it is, becomes an ion, right? So this is an ion now, and it gains an ion, an electron, and becomes an ion, a negative ion, or an ion, if you want to. Okay, so there it is. All right. Another thing to note is that because of those charges being there, they actually attract each other. These compounds attract each other. The positives attract the negatives, and the negatives attract the positive. And they form this kind of structure, which is known as a lattice. This lattice has a finite number, though. And you calculate that by noting the lattice energy of this particular compound. But that's another story for another day, much, much more advanced chemistry. But that's why the reason we don't have all the salt in the world in one big old crystal, right? It's because we have a finite amount of energy that can happen in this lattice. All right, next one is our covalent bonding. Covalent bonding is formed by the sharing of electrons. Again, there are two different types of covalent bonds. We have a non-polar covalent and a polar covalent. The difference we'll know later, much later, but for now, let's just say that as a general rule, the delta electronegativity, or the difference in electronegativity between the two atoms involved, is going to be less than 0.5 as a general rule. Like I said, there are exceptions. And then it is non-polar. But if it is higher than 0.5, and I found this in a textbook. So like I said, these are generalized rules. 1.6 to 0.5 are polar covalent. But the main thing to know is that they're all non-metals. So that's how we really know this is a polar covalent, or a covalent bond, is because they're both non-metals. So this is what happens. Two nonmetals get together. They have similar electronegativity because they're both on the same side of the periodic table, which is the shorter end, which is the right side, right? They are formed by sharing electron pairs. And yes, electrons are usually in pairs. So whenever we put electrons into something, we make pairs. The result, remember how before it was ionizing particles in all states? Well, in this case, they're not. They're non-ionizing, and they are not conductors, neither one. And they have low melting points. Think of sugar. Have you ever melted sugar to make caramel? You can on the stove, whereas salt, you cannot. So there's the difference right there. Anything that is covalent is going to be easily melted as a general rule. Again, sometimes they're a little bit harder, but they're easier than the ionic. All right, so here's a representation of the two atoms of, let's say this is fluorine. They're joining together. And how do I know it's fluorine? It could be chlorine, or it could be any of those that are on group 7, because that is representing the outer shell electrons. And there are 7. And notice how they're sharing that one pair, right? And they are not charged or anything because they have the same number of electrons that they need to have. Okay. Another way to represent it, remember, is that, you have the joining. So basically, think about you sharing a milkshake with somebody. You're drinking the milkshake and somebody takes a little more, that's a covalent bond, a polar covalent bond. If they take the same amount as you, that's a covalent bond. So that's basically how that works. All right, so in this case, I'm going to exemplify what a diatomic is. Diatomic atoms are those that come as a pair. They always come this way. And to remember them, there is a mnemonic device, and it is called Brinkelhoff. And why is it Brinkelhoff? Because it actually is all the elements that are. And let me make them white so that we can have, now we can see, Brinkelhoff. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine are all going to be diatomic. What does that mean? Okay, so that means whenever you see them in any equation, they're going to say O2, Cl2, F2, etc., etc., etc. They're always going to be doubled. Okay, that's what it means. All right, so and then where is a polyatomic ion? Okay, so this is a covalently bonded ion, because covalent compounds by sharing, and by sharing unevenly sometimes. And it depends. There's all kinds of levels of bonding in covalent. So when we are sharing those electrons, we can make all kinds of crazy stuff. And one of them is a polyatomic ion. And I'm going to show you where you can get your polyatomic ions. Hold on, I need my thing again. So when we are looking at polyatomic ions, we are going to get this reference, and I'll show you after we finish the PowerPoint, which is almost over. All right, so the next thing is a nonpolar covalent. Let me clear all this junk that I put up here. Just remember your Brinkelhoff, because that is important. Because when you're doing any kind of equations, you're going to have to remember their diatomic. Okay. All right, so nonpolar covalent is when electrons are shared equally. Again, anything that it's bonded to itself is going to be sharing equally. So any of these diatomics are going to be nonpolar, right? That's two oxygen atoms bonding together. I don't really like this one as much because there should be 4 electrons. Anyway, and that is an oxygen molecule. Polar covalent bonding, okay? So these are when they're shared, but unequally, like I was explaining, the milkshake. So water is an example. It's very polar. Why is that? Well, remember electronegativity increases to the right and up the periodic table, right? So fluorine being the most electronegative, look who's right next to it, oxygen. So oxygen is extremely electronegative, but hydrogen isn't. So when these two get together, oxygen acts like a little bit of a bully and grabs the electrons that hydrogen has and pulls them closer to itself than to hydrogen. So there's an imbalance of charges that is caused by this shift in electrons, but they're not shifting like totally transferring. No, they're not getting a positive and a negative charge. They're getting a partial, what is known as a partial positive and a partial negative, like that. See how it's just kind of, they're still attached, but they're pulling. That's exactly what that is. See how that big dog is pulling the little dog towards itself? Yeah, that's a polar covalent bond. Hydrogen's very lower in electronegative than fluorine. Fluorine pulls the electron from hydrogen to itself, therefore getting a partial positive and a partial negative charge. The positive is going to be the least electronegative because the bully, right, is the most electronegative. That's the one that pulls the hardest. All right, so water is very polar because oxygen, like I said, is more electronegative than hydrogen. Therefore, you get a positive region and a positive region with the hydrogens here, a positive region, and a negative region right here. So, okay, next. The next thing is a metallic bond. Metallic bonds are formed by metals only, and they are pretty strong. But it's weird that they're so strong because they are really only formed by metals, like I said, and only formed by their own metals. They, like iron is all iron, right? And aluminum is all aluminum, and so on and so forth. But the reason that is because they have such a big electron cloud due to all those d electrons that are in the middle, right? That they are going to be delocalized. Delocalized meaning nobody belongs to the other, right? They're all just being used by everybody. Okay, so you'll see in a minute what I mean by that. So they are very good conductors in any state. And they are lustrous, that means shiny, and they have very high melting points, even higher than ionic compounds in some cases. Just depends on the metal. All right, so this is kind of what, see how the dog is not even bothering to grab the bone because there's so many of them and they're constantly passing in front of him. So he knows that at any time he wants one, he can reach one. But that's kind of what a metallic bond looks like. See? Kind of looks like flies buzzing around, doesn't it? Yeah, it's kind of like that. They're just going all around the, all of the, these are the nuclei. So they're just going everywhere, just, constantly flowing. And that's it. Now, the other thing you notice is metals do not combine with metals. That's why we form what is known as an alloy, which is a solution of a metal in a metal. Some examples are steel, brass, bronze, and pewter, but the main thing is a homogeneous solution because you notice how there's a pattern to the combination, and that's why it's called a solution. All right. Oh, nope, no more of that. Okay, so now we are going to go to the part where I was telling you. We're going to get this area right here. This is called the crisscross method, and we're going to learn to write formulas. A little different. You don't have to do anything to learn it necessarily, except to just pay attention to the charges that are present in the atoms. And I'm going to make it bigger so you can see it. Okay, you can see that, I'm thinking. All right, so you notice that at each case, you got the ion formula and the ion name on the top and on the bottom, right? And then here, the ion formula, the ion name on the top and on the bottom also. Okay, so always put, so there are certain rules to making compounds. Always put the positive one first. So I'm going to just write with my hand oops, I don't know why it's doing that. It's been doing that and it's driving me crazy. Okay, sodium, positive. And then we have the chloride, right? Which is Cl negative. Okay, so the rule says always put the positive first, which we did, which is, in this case, is going to be the metal, right? Every time. And then take the negative ion, which is the chloride, and put it second. The second step is to take the charge without the negative or the positive, just a number of those two. And obviously that is missing, but we can always know that there's a one there, right? And put it as a subscript on the nonmetal, and take the number on the metal, on the non-metal, sorry, and put it as a subscript on the non-metal. So obviously this was unnecessary because this is NaCl and they're 1-to-1. But that's the rules, okay? So let's clear this out. And now you know why when I put them together, I just go ahead and put NaCl. And I'm just going to go ahead and start typing directly in here. So NaCl. That's that one. What about NaCO3? Okay, so this is carbonate. This is a polyatomic ion. When you have polyatomic ion, you treat the ion as a whole, okay? So basically, you do not separate them, you do not multiply them, you do not do anything to them except put parentheses around it. So in this case, the sodium is going to get the 2 from the carbonate, right? And the carbonate itself is not going to get but a 1. So there's no need to change anything. So we are definitely needing to do the subscripts though, and that's it. Now, as far as name goes, it's very easy. Sodium is the name of the ion, right, on the top. So we are going to just call them all sodiums, all of these. See, sodium, 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 because, oops, you do not. There's no sodium, sodium like that. There's sodium. All of these are just going to be their names. Okay, and it all starts with sodium because we are joining sodium with all of these guys right here in this one row. I mean, one column. No, it is a row. All right, so the next one is sodium and hydroxide. So it's a 1 positive and a 1 negative. So again, it's just NaOH. What about sodium sulfate? Well, we are transferring that charge from the sulfate, remember, as a subscript on the sodium. And then the SO4 just gets the SO4 because there's nothing to put on there because it's a 1. So why are we doing this? Remember I told you that compounds, ionic especially, have to add up to 0. All right, so let's say we have an atom of sodium. So we have one atom, let's just draw it like this. Okay, so we have an atom of sodium. And we have an atom of SO4. I mean, an atom, not an atom, unit. Let's just say a unit, a compound, but it's an ion actually of SO4. Okay, so we have those two. Now, in order for the compound to be neutral, we have to have 2 positives, right? So we need another sodium to counteract the negatives. Therefore, we write it as Na2. See, that gives us 2 of those. And then SO4, 1, right? Because we only need 1 of those. So you see, that's just telling me how many of each I need to make the charges cancel out. All right, so let's clear that. All right, so let's go and see the next one. Okay, so the next one is sodium again, right? And it's phosphate. So sodium, oh, come on, stop doing that. Okay, there we go. Sodium, and we have PO4. Now, oops, that's there, PO4. But this one has a 3 charge. Therefore, that's going to transfer to the sodium. It needs to be 3 of them to counteract all of those charges. Okay, so we need to put that as a subscript. And this one already has its own subscript, but the charges, so far we haven't had to use parentheses because it's sodium. All right, what about the next one? Sodium. There's no need to transfer anything because nitrate, oops, that's a capital O, O3. It's 1 to 1. So there's no need to transfer any numbers across. So now, as far as the name of this ion is chloride. So we said this is a combination of the 2. The name of this ion is carbonate. So this is a combination of the names of the 2 ions. See, very simple as far as the naming part, right? Because you already have it here. Now, later on, we're going to just have the compound and we're going to have to name it. But right now, we're just learning to put compounds together and kind of seeing where their names come from. So that when we are ready to actually do a name, we can do one like this. All right, so that's that. Okay, there's a polyatomic ion, and this is the only polyatomic ion that is what is known as a positive ion or a cation, right? All the polyatomic ions are going to be negative. If you notice, all of these on the top over here, all of these are negative. -2, -1, -2, -3, -1. But over here, we have ammonium. So the name of this ion is ammonium, which means that every single one of these its name is going to be ammonium. So we might as well just copy it down, right? And we just know that all of these are ammonium. That's how we start. And yeah, I'm not perfect on the amount of separation, but there you go. So all of those are ammonium. And then we're combining it with chlorine, right? So chloride ion, so ammonium chloride. See, there's the name. Now, how do we make it? Okay, same way. NH4 has a plus and Cl has a negative. So NH4Cl, that's it. I am going to lower this because it drives me crazy when I don't see a subscript. All right, next one. This is where we were talking about. Carbonate has a 2 negative. So NH4 is put in parentheses, okay, to symbolize that this whole thing is got to have 2 of those. All right, so we need 2 ions of NH4 plus for every 1 ion of CO3 negative. Come on, you. CO3. Come on. CO3. So, and you notice that the CO3 is not getting a parentheses because it's a 1. So just by it being there, right, it means that there is an ion in there. Okay. Next one would be ammonium hydroxide, so NH4OH, and I'm not doing all of these, but okay. So the next one needs a parentheses also, right? NH4, 2, and then the rest is SO4. All right, and yeah, I'm not doing all of these because it'll take forever for us to do that. Okay, so this one gets a 3, yes? Because the phosphate has a 3 negative, right? And then it's PO4. And then the last one is NH4NO3. Oops, that was supposed to be a 4, not a money sign. There you go. So that's all of them. So now the names: chloride, carbonate, and we're just not going to do all of them, obviously. This is just for you to practice if you want to do it for later. Hydroxide, okay, sulfate, phosphate, and see, it's just the naming the 2 ions, that's it, and nitrate. There we go. So that's all the names of every one of these compounds. Now, all right, now we have an ion of zinc. So zinc obviously is going to be all the way down, and I'm not doing all of these. I'm just going to do a couple of them. So let's just pick the ammonium one because it's interesting. And we're going to pick the SO4 and the PO4, and that's it. Just these 2. Okay. Oh, let's do the NO3 too. Okay, those 3. All right, so we're going to do zinc again, the rule. So I'm going to write them down. Zinc and chlorine. Okay, so zinc chloride. We are going to write down our ions, right? Which we know is zinc. And I'm just going to write it. Oh, why is it doing that? This is so annoying. Okay, so zinc. See, it's just, why is it? Okay. Zinc. And chloride, right? Okay, so again, that's a plus, that's not a 4, but it just had to make it. So crisscrossing, right? That gives me the zinc gets the 1, right? And the chlorine gets the 2, right? Because the 2 is up here and the 1 is over here. Okay, so then the atom the compound, sorry, is known as zinc chloride, and it is right here. Okay, so we're going to put it together. It's ZnCl2. See, this time the 2 came from the chlorine. I mean, the zinc to the chlorine. So we needed 2 of those to counteract the 1 charge of 2 plus. We needed 2 negatives to counteract that charge. And so we multiply the chloride ion times 2. That's all that means. All this subscript means how many of that particular atom we have. Okay, that's it. All right, so let's clear all these drawings. And let's go to the next one. Okay, so zinc and sulfate. All right, so let's look at this one. This one's interesting because it's a little different from what we've had before. And I chose it because of that. So we got zinc. Oh, come on, I'm trying. I cannot lift up. That's what's going on with this one. Zinc. And we have sulfate. Okay, so crisscrossing, right? We got zinc 2, parentheses, SO4, 2. Now, yes, you can simplify because what you're trying to show is the ratio between these two. And the ratio is a 1 to 1. You see that? Because we really don't need but 1 atom of each. So you can either do it this way. I like to do it on the actual charge itself. That way I don't have to rewrite the whole compound. So basically I say this 2 cancels out that 2, and that becomes a 1, right? So 1 to 1. All right, so let's clear that and rewrite the whole entire atom here. So zinc sulfate. So see, nobody needs any prefixes. You see that? I mean, any subscripts. I mean, prefixes. What am I saying? Prefixes. Subscripts. All right, the next one is zinc and phosphate. Again, zinc gets the 3, right? From the phosphate and phosphate. And yes, we do need to put parentheses because it is all of that, including the PO4, right, gets the 2. You see? So that's how we do the atoms correctly when there are multiple numbers. You've got to watch that you do not multiply because this is not a distributor property like math, and it's not P208, unless you're counting the number of atoms of each that are present, then yes. And the last one is zinc nitrate. Okay, so again, zinc is going to get the 1, and the nitrate is going to get the 2. And that's it. All right, now, there are some elements, and this is important too, that have more than one choice. What do we mean by that? Look at iron. Iron can be either a 3 positive or a 2 positive. Why is that? Because it's a transition metal. And I don't know if you remember when we made those ionic configurations, electron configurations for ions. Okay, we said that iron is going to be, oh, why are you doing this? This is so annoying. It never does that. Okay, so argon, right? And then we're going to have 4s2 and 3d. I think it's 6. Iron 1, 2, 3. Yeah, 6. Okay, so that would be it. So let's represent that looking at it like this so that we know where all these electrons are going and coming from. So that's your 4s's, and these are your 3d's, right? And 3d has 1, 2, 3, 4, 5, and this one is doubled. All right, so if we're trying to make an ion, the first ones that are going to be these, right? Oops, see, there it goes again. Undo it, undo it, undo it, undo it. See, it's like I did 14 different things, and I was doing the one and only the one. Oh, I have to do it one at a time, though. There we go. That's good enough. All right, so these are gone. we are going to erase these now. These electrons have been used. Those electrons are now iron plus 2, you see, because you have 2 less electrons. So this electron configuration right here would be that of iron plus 2, which is known as iron 2, so that we can differentiate between the two. Now, what if it's iron 3? Well, we have to remove the one that's paired, because remember, Hund's rule tells us, hopefully I can remove, oh, come on, eraser, oh, nope, it didn't let me. I couldn't remove just one, but as you can see, now it's missing 3 electrons, so now it becomes iron 3 plus. So how do we know which one we have if we don't mention it? Like if I say, make me a compound of iron oxide, and you're like, okay, iron oxide, iron and oxygen, but which one? I didn't tell you, did I? I didn't specify. So if I'm going to make iron oxide, okay, I said clear all my drawings. Okay, so I have to know, remember, I have to know which ion to use. We know oxygen is going to be at 2 negative, but what about iron? If I don't specify, what if I say iron 3 oxide? Then, oh, okay, I know that this is the 3 plus. Then when we crisscross, we can do Fe2O3. See? Or what if I say iron 2 oxide? Then I know it's the 2, and this time it's totally different compound, and you'll see that in a minute. When we crisscross, we get Fe2O2, right? And we can simplify to FeO. See? Look at the difference between these two, right? So we have to specify which compound we want to make by telling me in the wording of your compound name, iron 3 or iron 2. You notice how you've got a Roman numeral followed by parentheses. And this time, you notice it's not a 3 like this. It's a 3 in Roman numerals. And the reason that is so that it doesn't get confused with the 3 that is the other 3. Okay, so iron 3 is actually Fe2O3, right, in this case. So it makes a difference. So I can tell that that's the one I want. So in this case, that 3 stands for the valence electrons, or the charge, actually, the charge that is on that ion. Okay. So basically, these two are going to make 2 totally different compounds. If we were to make iron and what was the first one? Chlorine, right? That's going to be totally different. Let's see. Let's try to make iron chloride, iron 3 chloride in this case, right? So let's just do 1 and then we'll do the iron 2. So we are going to copy, okay? And that is going to be its name, right? Iron 3. And then the other one is chloride. Okay, I need that word chloride on here. So I need this one. Okay. Okay. Now, Fe doesn't get, because the Cl is 1, Cl gets 3. See? What if we're making iron 2 chloride? All right. So we got iron 2 right here. And then chloride. See, there is a difference now. I know which one to use. So in this case, it's going to be FeCl2. See, and I know that because that is telling me so. That Roman numeral is telling me which ion I need to use. Okay, that's all I wanted you to see. All right, so that's how you make compounds and how you arrive at their name also. Okay, next time we will see more on this, but it'll be more complicated because you will not have this nice little formula thing. You will just have your polyatomic ions. And this is what I was going to show you before you go, where this is located. Okay, you see how you've got all of these resources? Well, they're in the next one, but I need for you guys to print this whole entire packet, or at least have it handy. And there's your polyatomic ions right here. There's your whole list. It gives you almost everyone, but not all of them, because I couldn't fit them all in one sheet, and I wanted you to have just a single sheet. So you can see there's a ton of them. And out of those, only ammonium is the positive one. So there it is, ammonium ion, the only positive one out of all these polyatomic ions. All right, so make sure you print that. All right, that's it. We are done for the day. And I will see you next week. Wow, it is next week. All right, bye-bye.